Alrighty then, let's finish off section 11.1 and talk about the limits of sequences. You're going to find that you guys have already got a lot of the techniques and skills necessary for this part of the homework from Calc 1. So first note that if we graph a sequence in a coordinate system and then overlay its function on top of it, this is what we're talking about. So let's say you have a sequence and you're interested in going, what's the lim as n goes to infinity of a sub n? Well, that's the lim as n goes to infinity of 2n plus 1 all over 3n plus 4. Look familiar? Okay. Well, we weren't doing sequences, we were doing functions. Okay, so I'm going to do something elaborate that you don't have to do, but I'm going to do a quick sketch of f of x. And this is going to maybe hearken me back to, oh, I don't know, pre-calculus maybe. If we look at f of x, I'm going to do this as fast as I can. I don't know why I chose this one, but what the heck. Okay, what I notice in this one is it's got a vertical asymptote of, say, 3x plus 4 better not equal 0. So what we're getting is x itself better not equal negative 4/3. Horizontal asymptote, I don't know if you're privy to this. Horizontal asymptote, very quickly, I just look at the lead terms, and if they matchy, then I just simply say y is equal to the coefficients ratio, 2/3. Okay? I also notice that it's got an x-intercept at, say, let's see, minus 1/2 gives us 0. I'm looking at the top. It's got a y-intercept also, and that's when you plug in 0, you get 0 1/4. So that's a lot of information that you don't have to do right now, but a later section you will. Okay, so we may as well look at it. All right, so the graph of this thing, if we were to do a quick sketch of this, and we are being quick sketch artists here, let's pick a different color. Let's go with blue this time. Okay. It's got an x-intercept of minus 1/2, pretend that's there. It's got a y-intercept of 1/4, okay, fine. It's got a horizontal asymptote of, say, 2/3. And it's got a vertical asymptote of negative 4/3 over here somewhere. Okay, this is negative 4/3, and this is 2/3, etc. So where is the graph of this thing? I say that the graph is all over the map, I suppose. But if it's got this horizontal asymptote, then what's going to happen is if we were to graph this thing, it's probably doing something like this and cruising through those points and heading towards that asymptote like so. Okay, remember where we are? We're dealing with sequences. Who cares about all this graphing nonsense? We already did that in Calc 1. We're good with that, I hope. But here's the thing. The sequence itself, remember, is a function that goes from the counting numbers to the reals. And the counting numbers start here, and it's like this is 1, and this is 2, and this is 3, and this is 4. And if you plug those numbers in, if you look at the sequence, remember we did this guy already? 1 gave us like, oh, I forget. It gave us 3/7, and 2 gave us, oh yeah, I remember, 5/10. I remember the pattern. 7/13. Next one is like 9/16, and you can keep going. But these are ordered pairs. If you want to look at it that way, here's n and here's a sub n, just like a function. 1 gives us 3/7, and 2 gives us 5, not 5/10, but is it 5/10? Okay, 5/10, and etc. And where are those points? They're buried inside the continuous curve of this function. The point of all of this is to say, whatever the function does in terms of a limit at infinity, as n goes to infinity, or if x goes to infinity, we want to know what does a sub n do, is the same thing as what f of x does. So whatever this guy does, so does the sequence, because the sequence is a discrete set of numbers inside the function. All that to say that when they ask you to take the limit, and I'm going to go back up here and change my color to blue again, if it does it, yeah. Right here, we don't have to do anything like fancy with the limit. All we have to do is take it. So as n goes to infinity, you know what that is? That's like the horizontal asymptote. I do it really quickly. The answer is 2/3. You can see it in the picture right here. The sequence values are heading towards 2/3. But I don't know. You guys might have learned from a sticky teacher that said, you will always divide by the highest power. And that's fine. So you get like some work that looks like, okay, so what I've got is lim as n goes to infinity, and we've got like 2 plus 1 over n. I'm crowding it in there, I know. 3 plus 4 over n. And then you realize, hey, this guy goes to 0 when n goes to infinity. So does he, 0. So your final answer after all that work is, lo and behold, 2/3. So the limit of the sequence is 2/3. How you do it is up to you, okay? Sometimes, as I say up here, you have to use L'Hopital. It depends on the problem that this guy decided to give us, okay? All right, I wanted to show you the graph because I can do all the limit stuff I know how to do on sequences that I know how to do on functions. Great. So almost the end of this video is, let's find some more limits. Although some of them, look at this one, look at this one. Some of these are weird, okay? The first one, let's take a look at this guy. It says, in language. When a sequence has a finite limit, we say it converges to that limit. The word converge, diverge, they're going to be big to you guys. When the limit does not exist for a sequence, we say the sequence diverges, okay? So knowing those words, converge to a limit, you know how it is. Everybody converged on the last thing of toilet paper at the store or whatever. Or diverge. Everyone went their separate ways because there was no more toilet paper in the store. Ha ha. All right, so we're going to determine, this is the language, determine whether the sequence converges or diverges, and guess what? If it converges, find the limit, okay? All that really means is take the lim as n goes to infinity of each of these guys, 1 minus n squared. You can stop the video right now and try to do it yourself and see if you can do it. I'm just going to write this out and give you time to work it out too. Or, so go ahead and stop it if you want. This one might give you a hard time. It's not that terrible. Everyone struggles with that one with the factorials with good reason. And this lim is also n. Notice n goes to infinity the whole time. We're not letting n go to anything else. We're just wondering at infinity. You know what? That stands for the entire chapter. You don't have to worry about any other kind of limit except these. So let's do the first one. What I'm seeing here is, well, to spell it out better on a board, typically what I do is I go, this is 1 minus n squared. And if I multiply this out, I get 3n squared. I get like 1 and plus 4n, right? And plus 1. What am I going to do? I could divide by 1 over n squared, just like we do in Calc 1. But me, I'm so lazy, all I really do is I look at the lead terms and I can tell you what the limit is. I look at it as minus n squared over 3n squared, but ignore the n squared and say the limit is negative 1/3. What do you know? I did one. There you go. What I'm doing is I'm rapidly going through this, knowing you can pause this anytime you want. Let's go to this one. What's going on here? Well, the limit, what you could do with cosine, since it's continuous, is you can move the limit. Not that you have to write this, you could actually do it in your head, n pi over n plus 1, and work on that limit inside the cosine. Did you know that? That's pretty cool. So what I'm seeing here is lim as n goes to infinity. One of the things you could do is, since pi is just a constant, he can move outside. All you have to do is take the limit at infinity of n over n plus 1. Guess what? Here I go. Lazy bones. It's equal to 1. Aren't I cute? So what we have is cosine of pi times 1. Well, that's cosine of pi. Guess what that is? It's negative 1. So the limit there is negative 1. Everything is limit taking. It's not a difficult section unless you hate taking limits. Then it's like, here we go again. Except for the factorial. Remember, factorial. These are two factorials. I'm going to explain it this way. What if, I'll put this in like blue, or no, green. What if n, for example, as an example, n is equal to, I don't know, 5. Then n plus 1 factorial all over n plus 2 factorial is 5 plus 1 factorial all over 5 plus 2 factorial. So that's the same thing as 6 factorial all over 7 factorial. Did you know, looking up here, that the bottom number was 1 more than the top number without the factorial? So if n is 5, you get 6 over 7 factorial. 6 factorial over 7 factorial. If n is 21, then you have 22 factorial over 23 factorial. And watch how this cancels. This is really important. 6 times 5 times 4 times 3 times 2 times 1. Divided by, yes, 7 times 6 times 5 times 4 times 3 times 2 times 1. How do you cancel those things? It's a good question. This is how. Who cares? Who cares? These are canceling, cancel, cancel. Look who's left. Do you see that? He had one more oh, and the 6 is canceled. Look who's left. The 7 downstairs. So what I'm saying is you get 1 over 7. You know why? Because he had one extra factor. That's what factorial means. He has a 6 factorial, but he has a 7 factorial. Some people do this a different way. They go, oh, this is 6 factorial over 7 factorial, the same as 6 factorial over 7 times 6 factorial. And then they come in and they go, boom, and they go 1/7. That's pretty clever stuff. But now we're not dealing with actual numbers. We're dealing with the lim as n goes to infinity, n plus 1 factorial all over n plus 2 factorial. Nevertheless, this lesson of he's one more than the other guy helps you considerably. In fact, you could think about doing it this way. I'm going to write it out, though. I'm going to say it's equal to the lim as n goes, this is our last guy. No, it isn't. We've got n plus 1, and then we're going to drop down 1. So take away 1, n, take away 1, n minus 1, take away, till you get 3, 2, and 1. Downstairs, he starts 1 higher, n plus 2, take away 1, n plus 1, take away 1, n, and on down to 3, 2, and 1. So what you're going to see is, hey, look at the cancel, 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 cancel. And just like the 7th and how he survived, this guy also survives. And you end up with, I'm looking at the lim as n goes to infinity of 1 over n plus 2. And you know what that is. It's 0. And that's how you take that limit. Watch that factorial, man. That's good stuff. It's going to bug you until you got it down. Okay, we're going to see more and more of that one. So lastly, I just wanted to end this video by saying, I'm just going to introduce it. The monotonic sequence theorem says the following. Remember when I graphed that thing and I had a picture of the graph and it was going, okay, this guy, then this guy, then this guy, then this guy, inside a function or whatever? So this would be like 1, this is 2, this is 3, and this is 4. Okay, there's two things. One, monotonic increasing means it's always increasing. This is going to help us with series. So if it's increasing monotonically, it means it's always increasing. So that doesn't mean it does a little game like I'm going to jump down here and back up again. It doesn't do that. It has to keep increasing. Here's the thing. If on top of that you had some sort of max value, it is some sort of m, some number m that is an upper bound. It's the sequence is bounded above. Okay? If you are increasing and you're bounded above, here's the theorem, you have nowhere to go. You have to converge. You can't dip down and escape the fact that you are going to converge to some sort of limit L. I don't know what it is. So that's all it's saying. And we don't prove it. I don't prove it anyway. I just say, look, doesn't that make sense though? Think about it. Every time I add another number, it's a little bit higher, a little bit higher, a little bit higher. He can't go past the upper bound. He's blocked. He can't go negative. It's increasing. So he has to be tending towards a limit. And that's what this is saying. More on that later. I'll come back to that when we're doing series. And I think that's it for this video. I gotta shorten them, huh?